All right, so I wanted to make a quick video about this problem here. So we're talking about resonance, and we have quite a complex, I would say, structure here with a lot of different options. And the question we're asked is to find the three most contributing structures to the all of the possible resonance contributors. Okay, so with that said, it's worth it to classify a couple of things here. There's a bunch of rules that we want to keep in mind. These are kind of like the central commandments of resonance. We're always going to draw arrows from pi electrons and from lone pairs. And importantly, and I just discovered this because it's mentioned in chapter 8, is that we're always going to go towards either sp2 or sp atoms, because an sp3 atom like this nitrogen here, it's already full. It really doesn't have any room for any electrons, okay? Now keep in mind, we have a lone pair here that can go towards this sp2 carbon, but there's already a pi bond here, so it really doesn't make any sense. 4, 3, 2, 1, 0. There is a hydrogen here. However, I don't have this written, but one of the central tenets that we'll see of resonance is an oxygen that's doubly bonded, sucking up a pair of pi electrons, then kind of allowing room, and we can kind of see a lone pair here moving towards an sp2 carbon. It allows room for other things to happen, okay? In terms of the stability of resonance contributors, we don't want any charges if possible. So this contributor does not have any charges. If we do need to create charges, having a negative charge on the most electronegative atom, which in this case would be an oxygen, would definitely be preferable. So let's see what we can do here, and let's see if we can create some resonance contributors. The one thing you want to do is always make copies of what you're going to draw, and you just want to draw arrows on your original one. So a great place to start, forever and always, is going to be with this central commandment of moving pi electrons to, let's maybe not use red, of moving pi electrons to an oxygen. So that's exactly what we're going to do, and if we are collapsing pi electrons onto a lone pair, this is going to open up some room for another arrow. So we are going to draw an arrow from this lone pair. This would be good to create a pi bond. So let's see what happens when we do this. So first of all, if we collapse a lone pair here, is this going to create a charge? We have a valence number of 6 on oxygen, so 6, 5, 6, 5, 4, 3, 2, 1, 0, negative 1. It does, and that's okay, but we're going to create a negative charge here. And don't forget that there was a hydrogen on this carbon. So this carbon, for a split second in time, 4, 3, 2, 1, does have a positive charge, but we are going to correct that by moving the pi electrons from that nitrogen here. So this carbon retains a neutral charge, 4, 3, 2, 1, 0. It also retains being an sp2. This nitrogen, however, 5, 4, 3, 2, 1, and I'm just counting down the valence number there, is going to retain a positive charge. Not retain, it's going to create a positive charge. So this is okay. This is a valid resonance contributor. I'm going to draw a double-headed arrow to show that these two interchange between the two of them. So our total charge is staying the same because we have a neutral.
Are you tutoring or anything?
Yeah.
Oh. Can you make sure he's out of that bathroom like in 15 minutes?
Yeah, sounds good. Yep. So the interchanging between the two with this double-headed arrow. So this is a valid resonance contributor. This is good. We have a negative charge on an electronegative atom. So I would say this is a pretty valid resonance contributor. Okay, So can we make any other moves here, either from our original resonance contributor or from this one? Well, we do have pi electrons here that we could potentially move. However, I think I'm going to use this original contributor to build another one. Because this is kind of a structure with multiple directions, in other words, it's not like a linear thing where we kind of have like a conjugated system where we can kind of hop things to and fro. We kind of have this like fork in the road with this nitrogen. So let's kind of play with this. So what if we did this? What if, again, we start with our lone pair on this nitrogen and hop it here, again, towards an sp carbon. When we drew our arrow here, we were drawing along a lone pair towards an sp2 carbon. So again, that's what we want to look for, going towards the direction or towards a sigma bond that is attached to an sp2 or an sp carbon. So let's do the same thing here. If we draw that lone pair there, that would then kind of push some of these pi electrons collapsing onto this carbon. So let's see what happens. Let's see what happens if we do that. Let's erase this. All right, so our lone pair now becomes a bond here. It's going to push a set of pi electrons from what was a triple bond. Let's put this down here. Onto this nitrogen, which is okay. Let's see what kind of charges we create by doing this. All right, so do we have charges here? Well, we have a nitrogen with 5, 4, 3, 2, 1 with a plus charge here. And then the nitrogen over here, we have 5, 4, 3, 2, 1, 0, negative 1. All right, so again, a total neutral charge. This, interestingly, this carbon retains its sp hybridization because it still has 2 pi bonds. Now, is there a negative charge on the most electronegative atom here? No. However, other than that original move that we made, there's really no other way to make a resonance contributor with that oxygen. All right, so this is definitely a valid option that we can have here. Now, let's see, are there any other things we can do? We could potentially move like this pair of electrons from the pi electrons this way, creating like a triple bond. Let's give that a try, just for the sake of the sake of trying something. Let's give that a try, because this nitrogen now is sp2 hybridized. So let's just see. Let's play around and see what happens. So in this case, I'm going to use a different color here. We're going to pick these pi electrons and we're going to create a triple bond there. If we do that, we're breaking one of these, putting a triple bond here, 5, 4, 3, 2, 1, 0. It does create a neutral charge on the nitrogen. How about the charge over here? 5, 4, 3, 2, 1. It does create a neutral charge. However, we need to make another move here, because I don't think this by itself is actually, this by itself might actually be a valid resonance contributor, because a lot of times when you see a positive charge making one move is okay. Let's see, does everything 1, 2, 3, 4, 5, 6. Okay, so actually, no, we don't want to do this. And I'm going to tell you why. Nitrogen has too many electrons. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've overloaded its octet, all right? So we're going to abandon this line of reasoning. We're not going to make that move, because we want to make sure our octets are intact. And let's actually add that. Octets intact. And we can double check that with the one we just created here. We have 1, 2, 3, 4, 5, 6, 7, 8. Good. On this nitrogen, we have 1, 2, 3, 4, 5, 6, 7, 8. Octets look good there. Even on like this one here, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen looks good. All right. So let's start with, since we had success with starting with our original contributor here, let's start with that again, and let's see if we can move in a different direction. So again, we've kind of neglected what's going on up here. So let's see if we can create some action at the top. All right, let's again move our lone pair towards either an sp2 or an sp3 carbon. And real quick, like there's a lone pair here on this nitrogen, and there's definitely an sp2 carbon here. But it's already, you know, we can't create like a fourth bond. Like there's really no, that's kind of what we tried to do before. And it's just really not going to work. So in this case, let's move the lone pair to this bond that is connected to this sp2 carbon. And that is going to push these pi electrons to this carbon here. So if we do that, let's see what we get. I'm kind of running out of space here, but we are going to create a pi bond here. We're going to get rid of these electrons, and we're going to create a lone pair. And keep in mind, there were 2 hydrogens on this carbon. And now we do have a lone pair that we just put on it, which is fine, which is okay. It creates an sp3 carbon there. Let's just draw a little line so we know we're not confusing these. All right, let's see if we have any charges. So with this nitrogen, we have 5, 4, 3, 2, 1. So we do have a positive charge on the nitrogen, which means we probably have a negative charge somewhere. And this carbon here, we have 4, 3, 2, 1, 0, negative 1. Yeah, there's our negative charge on this carbon. So this is a valid resonance contributor. So really in total, this was our first one. This was our second one. And what we just created here is now our third one. And keep in mind, the resonance contributors that we created were just moving the lone pair of this original nitrogen and giving each of these sigma bonds, here's 1 here, here's 2 here, and now here's 3 here, giving each of those sigma bonds a turn at sharing those electrons in a pi bond. So it's kind of cool the way that this ends up working. And all of our rules, even this carbon with a negative charge, 1, 2, 3, 4, 5, 6, 7, 8 has a full octet. Nitrogen 1, 2, 3, 4, 5, 6, 7, 8 has a full octet. We have a neutral charge, which is what we had initially. We are drawing our arrows from pi electrons or lone pairs. The initial move here was from a lone pair towards an sp2 carbon. We did do a move here where we moved it towards an sp carbon, and we're keeping our octets intact. So I would say that the most contributing of these structures would definitely be this first one, the first alternate contributor we created, because oxygen has a negative charge, which it can handle better because it's so electronegative. Certainly the very first one we started with, it has no formal charge on it. So that would be relatively stable. But what about between 2 and 3? Which one of those would we say is more stable? A negative charge on a carbon is never a good look. A nitrogen is certainly more electronegative than a carbon. It's not quite as electronegative as an oxygen, but I would make a very strong argument that 2 is definitely more stable than 3 because of the fact that our real big comparison here is negative charge on nitrogen or negative charge on carbon, and I would certainly prefer that to be 2. So there you have it.